At the center of our galaxy, there is a place where the laws of physics are being tested at their absolute limit. A place where stars orbit in visible darkness at millions of kilometers per hour. Where space itself is being torn, twisted, and consumed. Where time, as we experience it, would cease to have any ordinary meaning. It is not a metaphor. It is not a theory waiting for confirmation. It is there, right now, 4 million times the mass of our Sun, compressed into a region smaller than our solar system, sitting at the heart of the Milky Way, approximately 26,000 light-years from where you are standing. The question is not whether this region is dangerous. The question is how dangerous and to what. We tend to think of our galaxy as home, and in a very real sense, it is. Every star you have ever seen with your naked eye belongs to this structure, a vast, slowly rotating disk of gas, dust, ancient light, and roughly 400 billion suns. But a galaxy is not simply a collection of stars floating peacefully in space. A galaxy is organized, structured. And at the center of that structure, something ancient and extraordinarily powerful has been shaping everything around it for billions of years. Understanding what lives at the center of a galaxy and what it does is not merely an academic exercise. It is, in a profound sense, the story of why galaxies exist at all, why stars form where they do, why certain regions of the cosmos are fertile with planets and life, and others are scorched, irradiated wastelands. The galactic center is not a distant curiosity. It is the engine of our cosmic neighborhood, and like any engine, it has consequences, some of which reach far beyond the machine itself. To understand the most dangerous region of a galaxy, we need to begin not with destruction, but with gravity. Because gravity, more than any other force in the universe, is the architect of everything we are about to discuss. In our everyday lives, gravity is gentle. It holds us to the ground. It keeps the moon in its orbit. At the scale of a solar system, it is graceful. Planets tracing ellipses, moons following their paths in a kind of slow cosmic choreography. But gravity has no upper limit. The more mass you concentrate into a smaller space, the stronger gravity becomes at that surface. And if you compress enough mass into a small enough volume, something extraordinary happens. A threshold is crossed. The escape velocity at that surface reaches the speed of light. Nothing, not even light itself, can escape. And what was once simply a dense object becomes something categorically different. We call it a black hole. Now, a stellar mass black hole, formed when a massive star collapses, might contain 5, 10, perhaps 30 times the mass of our Sun. These are already objects of extraordinary gravity, surrounded by regions of space from which there is no return. But at the centers of galaxies, something far larger exists. These are called supermassive black holes.
Let that settle
and the
for a
one
moment.
at the center of our
4
galaxy,
million
known as
suns
Sagittarius
worth of mass,
contains
occupying a volume
approximately
that would
4
fit
million
comfortably
solar
within
masses.
the orbit of Mercury around our Sun. And this, in the cosmic catalog of supermassive black holes, is actually considered modest. There are galaxies harboring black holes 1 billion times more massive than our Sun, 15 billion times more massive. We have now imaged one of them, M87 star, the black hole at the center of the Messier 87 galaxy, whose shadow was first photographed by the Event Horizon Telescope collaboration in 2019. But let us stay close to home. Let us talk about what actually happens in the region surrounding Sagittarius A star. When astronomers and physicists speak of the galactic center as dangerous, they are not speaking of a single hazard. They are speaking of an environment layered with overlapping threats, each one alone capable of sterilizing life, Together, they create a region of the universe that is, by any reasonable measure, incompatible with the kind of stability that life requires. Let us walk inward. Imagine you are approaching the center of the Milky Way from our position, 26,000 light-years out. As you travel inward, the first thing you would notice is density. Stars become more closely packed. What in our neighborhood might be several light-years between stellar neighbors becomes fractions of a light-year. Eventually, within the innermost few light-years of the galactic center, stars are so densely packed that the night sky, if you were standing on a planet there, would never be dark. The collective light of neighboring stars would rival our sun's brightness multiple times over. This alone is not necessarily lethal, but it is a sign of what is to come. Moving closer still, within roughly a light-year of Sagittarius A star, you enter what astronomers call the central parsec. Here, you find a remarkable population of young, massive stars called the S stars, orbiting the central black hole in tight, fast ellipses. The fastest of these, a star called S2, completes a full orbit around SGR A star in approximately 16 years. At its closest approach, it travels at nearly 3% of the speed of light. 3% of the speed of light. That is not a figure our intuitions are built to handle. It is approximately 30 million kilometers per hour. And yet, from a distance, watching through telescopes, S2 traces its orbit with an almost mathematical elegance. This observation, stars orbiting an invisible point with precisely the dynamics predicted by general relativity, was the smoking gun that confirmed the existence of a supermassive black hole at our galaxy's center. It earned the scientists who led this work, Reinhard Genzel and Andrea Ghez, the Nobel Prize in Physics in 2020. But these stars orbiting at extraordinary speeds are not the primary source of danger. Let us talk about radiation. Massive stars, the kind concentrated in enormous numbers near the galactic center, live fast and die violently. They burn through their nuclear fuel in millions of years rather than billions. When they die, they explode as supernovae, releasing in a matter of seconds the equivalent of what our sun will radiate over its entire 10 billion-year lifetime.
A single supernova, if it occurred within roughly 30 light-years of Earth, would be capable of stripping our ozone layer, flooding the surface with lethal ultraviolet and X-ray radiation. At the galactic center, supernovae are not rare events separated by millions of years. They are relatively frequent, and their remnants overlap, filling the region with expanding shells of hot ionized gas and high-energy particles. These high-energy particles, cosmic rays, propagate outward from the galactic center in all directions. They are protons and atomic nuclei accelerated to near-light speeds by the violent magnetic environments of supernovae and other energetic events. They carry enormous energy, and they interact with matter and with magnetic fields, generating secondary radiation of their own. The galactic center is effectively bathed in an intense flux of X-rays, gamma rays, and cosmic ray particles, at levels many orders of magnitude higher than what we experience in our relatively quiet corner of the galaxy. But there is still more. Now let us approach the central object directly. Surrounding SGR A** is a structure that forms when matter falls inward, an accretion disk. Gas and dust drawn toward the black hole do not fall in directly. Angular momentum, the same property that keeps a spinning figure skater rotating, causes infalling material to spiral inward, forming a flattened, rotating disk of superheated plasma. As material moves through this disk, it collides and compresses. Friction heats it to temperatures of millions of degrees. At these temperatures, matter radiates intensely across the electromagnetic spectrum: X-rays, ultraviolet, optical light. For the most actively feeding supermassive black holes, called quasars and active galactic nuclei, this radiation output can exceed the combined light of every star in the host galaxy. Sagittarius A** is, by the standards of supermassive black holes, remarkably quiet. It is currently in a low accretion state. There is relatively little material falling in. But even in this quiet state, it produces periodic flares of X-ray and infrared emission, sudden brightenings that last minutes to hours, likely caused by small clumps of material spiraling in and being heated to extreme temperatures. There is observational evidence from structures called Fermi Bubbles, enormous lobes of gamma-ray emitting gas extending above and below the galactic plane for roughly 25,000 light-years, that SGR-A* was significantly more active in the geologically recent past. Perhaps a few million years ago, it underwent a period of intense feeding, launching jets of energy perpendicular to the galactic disk in an event that left its fingerprints across a significant fraction of our galaxy's volume. And then there is the most intimate form of danger, the tidal force. If you were to approach a black hole, the difference in gravitational pull between the side of your body closer to it and the side farther away would grow increasingly severe. Gravity falls off with distance. The near side experiences stronger pull than the far side. This differential force stretches objects along the radial direction and compresses them laterally.
For small black holes, this tidal force becomes lethal well outside the event horizon, the boundary of no return. For supermassive black holes, the mathematics changes in a counterintuitive way. The tidal force at the event horizon is actually weaker for more massive black holes because the horizon itself is so much larger. For a black hole the mass of Sagittarius A, you could, in principle, cross the event horizon without immediately being torn apart. But you would be inside, and inside is another story entirely. The event horizon is not a physical surface. There is no wall there, no membrane you could touch. It is a mathematical boundary, a threshold defined by geometry and gravity. At that boundary, the escape velocity equals the speed of light. 1 centimeter inside, and no signal, no matter, no information can ever return to the external universe. For an outside observer watching someone fall toward a black hole, something extraordinary happens. Due to the extreme warping of space-time near the event horizon, light emitted by the infalling observer takes longer and longer to climb out. The observer appears to slow down. Their image reddens as light is gravitationally red-shifted. They appear to asymptotically approach the horizon, freezing there in an infinitely elongated final moment, never quite arriving from the outside perspective. But from the infalling observer's own experience, from their proper time, they cross the horizon in finite time. They may not even notice the moment of crossing for a large enough black hole, but they are now inside. And inside, the singularity, the region where our current laws of physics break down, lies not in a specific direction of space, but in the future. It is a moment in time, not a place, and it is unavoidable. This is one of the most profound results of general relativity. Inside a black hole, space and time exchange roles in a certain mathematical sense. The singularity is not somewhere you can steer away from. It is when you are headed, as inevitable as tomorrow. Here is the truth that most people do not expect when they first encounter it. The galactic center, this extraordinary engine of violence and radiation, is not wholly destructive. It is generative. The same supernovae that irradiate the surrounding region are the furnaces in which heavy elements are forged: carbon, oxygen, iron, silicon. Every element heavier than hydrogen and helium that makes up your body, your planet, your ocean, was assembled in the cores of massive stars and scattered by their explosive deaths. The galactic center, with its dense population of massive stars and high supernova rate, has been producing these heavy elements and distributing them throughout the galaxy for billions of years. The outflows driven by stellar winds and supernovae carry metal-enriched gas outward, seeding the outer regions of the galaxy with the raw materials for rocky planets and eventually complicated chemistry. There is a deeper irony still. The supermassive black hole at the center of a galaxy is not merely a destructive force. Current models of galaxy formation suggest that the feedback from active supermassive black holes, the jets, the radiation, the outflowing winds, plays a critical role in regulating star formation. When a black hole feeds too aggressively, its energy output can heat and expel the gas that would otherwise collapse into new stars. Without this feedback mechanism, simulations suggest galaxies would form stars far too rapidly, consuming their gas reserves in a fraction of the time, collapsing into configurations far less hospitable to long-lived, stable solar systems. The violence at the center of a galaxy, in a very real way, is part of what makes the quieter outer regions possible.
We exist in the quiet because the center is not. Let us step back now, all the way back. We are orbiting the galactic center at roughly 220 kilometers per second. Our solar system completes one orbit of the Milky Way approximately every 225 to 250 million years, a period sometimes called the cosmic year. In the roughly 4.5 billion years since Earth formed, we have completed perhaps 18 to 20 such orbits. We are not stationary, we are passengers. And our position in the galaxy, roughly 2/3 of the way out from the center to the edge of the disk, is, from a habitability standpoint, not accidental in the sense of being arbitrary. It places us in what some researchers have called the galactic habitable zone. Far enough from the violent, radiation-intense center, far enough inward to have benefited from the heavy element enrichment that the inner galaxy's stellar generations have produced, a kind of cosmic Goldilocks position. This does not mean life cannot exist elsewhere. The universe is vast, and we have sampled almost none of it. But it does suggest that the architecture of a galaxy, the violent center, the structured disk, the quiet outer reaches, may itself be a kind of filter, selecting for regions where stable complexity can persist long enough for something like biology to take hold. The galactic center reminds us that the universe is not uniformly hospitable. It has texture, gradients of danger and calm, and life, wherever it arises in the calmer regions, not because the violent regions do not exist, but because in the violent regions the timescales for stability are simply too short. Stars near the galactic center are disrupted. Planets, if they form at all, are perturbed by close stellar encounters before they can settle into stable orbits. The radiation environment is orders of magnitude more intense than what we experience. The very crowding of the center, which makes it so visually spectacular, makes it so hostile. And yet there is a humility in all of this that I think is worth sitting with. The black hole at the center of our galaxy has been there doing what it does for billions of years, long before Earth formed, long before the first simple cells appeared in shallow Archean seas, long before the first human being looked up at the night sky and wondered what was there. It will be there long after we are gone. Not because it is indifferent to us in any moral sense. It is simply a physical object, obeying the equations that govern space-time. But there is something philosophically bracing about that. The most powerful gravitational object within tens of thousands of light years has been quietly shaping the structure of our galaxy for cosmological timescales, and the most we knew about it until very recently was a faint radio source in the direction of the constellation Sagittarius. The universe keeps its most important secrets not by hiding them, but by placing them at scales and distances beyond our ordinary experience. We had to build instruments of extraordinary precision, radio telescopes spanning continents, infrared observatories above the atmosphere, detectors of sub-millimeter radiation capable of resolving features 26,000 light-years away before we could begin to see what had been there all along. That is the nature of physics. The universe does not simplify itself for our benefit. It asks us to extend our instruments, our mathematics, and our imagination to meet it where it actually is. There is a thought I return to often when contemplating the galactic center.
Somewhere in that dense, irradiated, gravitationally extreme region, stars are completing orbits that last decades. Gas clouds are falling toward an event horizon from which they will never return. Flares of X-ray emission are briefly illuminating the surrounding parsecs before fading back into the low hum of background activity. And here we are, in the outer disk, warm, stable, orbiting slowly enough that the nearest star is years away at the speed of light, living on a rocky planet with a magnetic field and an atmosphere and water. The distance between those two environments, the violent center and the quiet periphery, is not just spatial. It is the difference between a universe in which complexity persists and one in which it is continuously erased. We are here, in part, because out there something extraordinary is happening. The most dangerous region of a galaxy is not simply a warning, it is context. It tells us something about the conditions under which we exist and about how finely threaded the path to stability actually is. The universe, in the end, is not hostile to life, but it is not designed for it either. It is simply vast. And in that vastness, there are places of extraordinary violence and places of extraordinary quiet. We are in the quiet. For now. If this journey to the edge of what physics can describe left something resonating in you, consider subscribing, not for the frequency of uploads, but for the depth of what we explore together. Every video on this channel is an attempt to close the distance between where human knowledge currently stands and where the universe actually is. If that is the kind of thinking you want more of, then stay with us. And if there is a question about the cosmos that you find yourself returning to, leave it in the comments. The best questions are the ones that refuse to be answered quickly. Those are the ones worth making a video about.